So now we're going to start thinking about what happens to the beam and what deformation does the beam have. So today, we're going to do the simple stuff. So today, we're going to consider, to get started, a case in which my bending moment is constant. I better get used to do these curly M's. I keep going into ends. OK, so somehow M's are more kind of challenging for me to do. So the bending moment that we're dealing with today, we're going to start by considering a constant bending moment. Constant. And we're going to start by, as we always do, by considering a beam which has constant cross-section and just one material, length L. So constant cross-section, et cetera, et cetera. Just nothing changes along the length of the beam. We always start like that when we want to kind of get a grip on what's going on. OK, so what happens to the beam when I apply a moment at its end? If I take the beam, you can see what happens. I mean, it's not really earth-shattering news, right? I take the beam, and I apply a moment at the end. It curls up. You see, if I go here and it's attached to the wall on this side, this is my wall right here, and I take a moment and I do that, it's going to curl up, right? That's the deformation that's going to happen. So now I need to describe what is the deformation. So when we had our problem in torsion, remember, we measure what happens to the beam by saying it rotates, the end of the beam rotates by an angle. Remember, we call that angle phi, the rotation at the end of the beam. Now, the angle, something rotates as well. What rotates is the end of the beam. Let me make it rotate even more. What rotates is the end of the beam. But the rotation now, instead of being along the axis of the beam, is going to be with an axis of rotation, which is z, right? So now the end of the beam has rotated. And this angle here, which is how much the angle of the beam has rotated, that is our measure of deflection, if you want, of the beam. Is a measure of how much the end of the beam has changed with respect to the undeformed configuration. So for torsion, we were calling the angle of twist of the shaft, we were calling capital phi. For bending, the rotation at the end of the shaft is called capital theta, another Greek letter. Remember, capital phi for torsion, we had this guy, vertical down. This is capital phi. In bending, we have this guy here, horizontal. If you want, you can even put the bars like that. And this is the capital theta. Theta, whatever you say. OK? So this angle here is the deformation. But actually, if I have to be careful, the deformation, right? Our deformation was not just measured by how much the end of the beam rotates or how much the beam elongates. When we had axial loading and we had delta for the elongation, we did delta over L. When we did torsion and we had phi, we did phi over L. So similarly now, the deformation of the beam is measured not just by how much it rotates, but how much it rotates per unit length. So the deformation is really phi divided by the length of the beam. Because, of course, if the beam is very long, it can get a good angle of rotation without too much deformation. But if I have a stubby beam, to get that angle of rotation, I need a very large deformation, right? So my deformation is always per unit length. In axial loading, delta over L. In torsion, phi over L. In bending, theta over L. So let me show you something very convenient for bending. Let's say that I introduce rho, the radius here. So I see that the beam curls up. Because everything is uniform, the same moment, the same cross-section, nothing changes along the bend of the beam, they all curl up by the same amount. So the whole thing is going to curl up in a circle, in an arc of a circle. And the radius of this arc of the circle, I call it rho. And you can see that the length of the beam, which is L, so I started with a beam, I just draw it very curly, but you know that in 201 we don't do that much deformation. But if the length of the beam is L, after it curls up is L, so I can say that the length of the beam is equal to theta times this radius rho. Or another way of saying this is that my theta over L is equal to 1 over rho. See? 1 over rho, this guy, triple stars gets. This is the star of bending. This is the measure of deformation in bending. It's called the curvature. Why do we use curvature, 1 over the radius instead of the radius, to measure deformation? Because we want something that tells us that if the deformation is big, our measure of deformation must be big. So if you have something which is originally straight, if something curls up a lot like this, it will have a small radius, but a big 1 over rho. If something curls up just barely like that, so that the radius is going to go all the way up to the 4th floor, right? So the radius is big. 1 over rho is small. So the angle per unit length, which is 1 over the radius of curvature, 1 over the radius of curvature, and that is called the curvature. That is our measure of deformation, because when this one is big, it means that there is a lot of deformation. When that one is small, there is no deformation. In this case, if it doesn't deform at all, what is the radius of curvature of this guy? 0. So 1 over the radius of curvature is not 0. The radius of curvature is infinity. The curvature is 0. It doesn't curve. Okay, 1 over rho is 0. The radius is ginormous, right? This one is a big radius. This is a big rho. This is a small rho, but big curvature, big radius, small curvature. And so this thing here is our star of the game, is the measure of deformation, 1 over rho, the curvature of the beam. Okay? The same way as when we were defining elongation and we were defining the sign of the elongation, we said the elongations are positive. When the bar gets longer, we need the sign for the curvature. So what is the sign of the curvature? Based on the sign of this moment here, what do you think we're going to consider positive curvature? Sad beam, happy beams?
Happy beam.
Happy beams are going to have positive curvature. Told you bending is like a riot. It's fantastic, okay? So positive curvature, this is a positive 1 over rho in the xy plane, right? So this is a positive curvature in the xy plane, positive if it corresponds to a smiley beam, which corresponds to the bending moment. Curvature and bending moment go together, the same way as elongation and axial force go together, the same way as angle of twist per unit length and torque resultant go together. Same conventions. Okay. Now, there is something that happens when the beam curves. And what happens is that strain happens in the beam. How do we see this? It's fairly straightforward. If I draw the beam deformed, and now remember that I'm doing all these drawings, making chunky beams, right? Deforming a ton, short and stubby, But I do it because that way it makes my drawing easier. But remember, in your mind, the beams are slender, like fashion models, fashion model beams. OK, so this is our beam curled up. Now, look at this thing. If I look at the radius at the top of the beam, and if I look at the radius at the bottom of the beam, they cannot be the same, right? It curls up. They have different radii. So if I go and look at the bent beam, and if I want to, so this is it. You see, the radius on the top and the radius at the bottom are different. They are different by the thickness of the beam, exactly. So if I go and I want to go with my little tape measure, and I measure now how long is the top of the beam now that is deformed. So the length at the top is equal to, this one is still our good friend, our new friend, the angle theta, right? So that's still, that's a little too much of whiskers. Let me forget the whisker. This is angle theta. So this angle here is still my angle theta. The length at the top is going to be, OK, I'm running out of voice here if I'm going to scream against creation. OK, so this angle here is still our friend, the angle theta. So if we know the angle theta and the radius, I can find how long is the length along the top of the beam. The length at the top is going to be equal to theta times radius at the top. The length at the bottom, if I go here with my little tape measure and I see how long is the bottom of the beam now, the length of the bottom is equal to this angle theta times the radius at the bottom. They're not the same. Yes?
Which one is rho?
Rho is right at the middle. Rho is in the middle, and we're going to get to that right away. Rho is the radius in the middle. On average, they have a radius rho. But on top, I have our top, and at the bottom, I have our bottom. These two guys cannot be the same. They're different. So if they are different, there has been some axial strain, right? There is no way around it. So there must be some axial strain, because things have changed length. Things cannot change length without being strained. And so if there is some axial strain in this beam, I have to figure out how much it is. But if there is some axial strain, what else is going to be inside? If I got strain, what do I pay with? Stress is the coin. Axial strain means I have axial stress. I must have axial stress. Whoa, I say, there is axial stress, and I'm not giving any axial force. My N, my axial force, is zilch, 0, right? So how does that work? If I have my cross-section of the beam, I'm just looking at it now, because I'm interested about what's going on. I'm looking at my cross-section, and I say there must be strain in it. And I know that the total must be 0. So what does that mean? It means that there must be both tensile and compressive stresses. And together, they must sum up to 0. So we see that the bottom is getting longer. So at the bottom, where things get longer, what kind of strains are they going to be there? Tensile or compressive? Tensile. So the bottom of the beam is going to have tensile stresses and strains. The top of the beam, things get shorter. I must have compressive, right? So the top of the beam must be compression. Compressive situation on the top, tensile situation at the bottom. So they get together, they give me 0 axial force resultant. How about the middle? How about right at the middle of the beam? What happens there? right along this line here, if I look in the xy plane, or if I look, so this is my x-axis coming out, this is my y-axis coming out, and this is my z-axis. What happens right in the middle?
That stays at L.
That stays at L. Absolutely right. These guys here in the middle say, I cannot be tensile. I cannot be compressive. I cannot decide. I'm going to stay neutral, like Switzerland, right in the middle here, right? I'm not going to get involved with your strife, who's tensile, who's compressive. I'm going to keep all the money and stay out of it, okay? So the middle of this guy, this is the neutral axis. So here, the middle, very important. I need space here. So this is neutral, right at the middle here. And actually, what we do is, for convenience, we set y equals 0 right at the neutral axis, in the middle. So now the fact that we cheat and we only deal with symmetric beams, that makes our life easy, because there is always going to be a top equal to the bottom, right? So if I want to balance the compressive stress in the top and the tensile stress in the bottom, as long as the sections are symmetric, I know that the middle is the one that's going to be a 0. So for all our beams in 201, the neutral axis is always going to be right at the axis of symmetry of the beams. These are all the neutral axes of the beam. Neutral, Switzerland. Okay? Stays at 0. And essentially, the consequence is that now this length here remains exactly the same length as it was before it started deforming. The things on top get longer than the original length. The things at the bottom, the things at top get shorter. The things at the bottom get longer. In the middle, couldn't care less. Stay the way I was. And so with this information now, I can calculate how much the strains are.